Okay, we're very happy to have here Will Zeng from Goldman Sachs, and he's going to talk to us about challenges in QNLP. I hope both near and long term. Take it away.
Great. Thanks so much, Constantinos. So I'm the last talk of the day, and so this will be a little bit short to give a little bit of a perspective. I did a little bit of stuff in quantum natural language processing back in the day with Bob, but haven't been working in it too actively. But I have been thinking about quantum advantage a lot. And so the talk is mostly about, well, if we're really looking to find quantum advantage for natural language processing tasks, how should we think about that? And it really starts with, well, what do we mean by quantum advantage? So the framework for this, the one framework that I like to bring to this is that there's sort of a quadrant to look for. And maybe most recently, what people have been hearing about are some kind of quantum supremacy benchmark or terminology. And so what this means is that for some problem, there's a foundational difference between what you can do with a quantum computer and a classical computer. So in this case, it means we have a proof up to at least some reasonable computational complexity assumptions that the quantum solution to the problem is more efficient than the classical one. And in particular, it might be, maybe we say it has to be a super polynomial speed. But this is, of course, for any problem. So in the Google's recent announcement, it was reported Thomas sampling, which is just some random statistical problem that we have maybe one application for in certified random numbers, but not broad application. So there's also a practical version of advantage, which is just to say that you do something that's better with a quantum computer in terms of wall clock time, and you don't care about the computational complexity at all. And so here heuristics matter. Constant factors, of course, matter, but also that's what really matters if you're trying to make a technology that's useful. And so maybe for any problem, that would be weak quantum supremacy. And then if you switch to problems that are valuable and useful for someone, not just a mathematical problem, then I suppose we call that quantum advantage or strong quantum advantage. So strong quantum advantage is a valuable problem that you have a computational complexity theoretic proof that you can do better. And you need to be able to exhibit that advantage on a quantum computer as well. You can't just prove it as possible. You need to actually show the solution. So in particular, these practical improvements, the weak quantum supremacy or quantum advantage, are really difficult when hardware limits the kind of empirics that we have access to. And this really distinguishes the search for quantum advantage in natural language processing or machine learning from stuff that happens classically. But we can learn a little bit from what's happened with classical hardware. And I think we need to, as we think about research towards quantum advantage, we need to know the game that we're playing. And there was a really recent paper called the Hardware Lottery by researcher Sarah Hooker at Google Brain that I think is worth looking at. And it's speaking in the context of classical neural networks and pointing out that a research idea sometimes wins not because it's the best idea, but it's because the one that's available, that's able to run on the available software and hardware, so that you actually can do empirical studies when theory, leaves you wanting. And as the example, they point out that most of the algorithmic components for deep neural networks had been in place for decades before the hardware available scaled up to allow us to do the kind of things that folks have done in the last few years. And this very much might be the case in quantum, and it might be the case in quantum natural language processing in particular, where we're coming up with very good ideas and algorithms, but it's going to be a long time until we can empirically test them to find advantage. So a little bit about just about me and about quantum advantage, how I think about it in finance. So I joined Goldman relatively recently. We're starting a group here that's looking at how to apply quantum computers usefully in finance, and how are we trying to do that? And this might be useful for how to think about how to do it in natural language processing too. So you want to work backwards. What is the problem you're trying to solve? What performance is needed for that to actually be valuable and useful? And so then you need to ask, what are the quantum resources that are required to reach that valuable advantage? And this is not, when you talk about going to real constant factors, numbers of Toffoli gates, the actual distance of the error correcting code you need, or something like that, it's not very well known for many problems. I mean, we know it for Shor's algorithm. We know it for, and that changes every few years as people improve it. And we know it for some things in quantum chemistry, but it hasn't been studied in many, many domains. One of the fun things about finance is that there's often a close connection between technical improvements and useful value. So a few algorithmic improvement percentages can be valuable quickly. And the downside of financial applications is that they're not obviously quantum native. And that second thing is something that natural language processing might be as well. It's not obvious that it is a quantum physical model, but there are some analogies like we've all seen today, and then I'll talk about more. So the kind of things that I look at are Monte Carlo and optimization. And the pieces are to ask, what are the resources that we need to achieve that advantage? How can we design algorithms to do it? And then what's the hardware that's actually going to get us there? And hardware, I mean sort of architecture more broadly, because it's not likely that general purpose QRAMs and quantum computers, bolt-on quantum computers are going to be available soon. So let's jump into natural language processing. So there's really, to simplify a lot, I think two paths that are not necessarily mutually exclusive. You can either accelerate classical methods, or you can introduce new, better quantum models and methods. And there's kind of two parts inside of the quantum side. You need to, if you have a new method or a new model, you need to show that it's actually better for natural language processing, perhaps in some specific tasks. And then you need to show that quantum speeds it up. So there's sort of these two stages. So this is one, the promise of DisCoCat is sort of this, and its extended family of children, is that it might be a new and better quantum-ish model for NLP. And sort of the motivating intuition, as has been talked about today, is that bag of words models don't take into account the compositional structure of grammar. If we move from vectors into tensors, then we can add algebraic structures on top that allow us to do rewrites, grammatical rewrites, things like this. But the cost is that you're now in a larger space. But you can deal with the larger space if you have a quantum computer. And this is all illustrated lovely in a graphical form by Konstantinos's nice kind of animation here. So this is the appeal of the, let's say, quantum model approach. But a thing to keep in mind is that new classical methods are actually working very well. And so I have colleagues who are not quantum people, who are NLP people, and I tell them a little bit about the stuff that's going on in DisCoCat, and sort of here's what they come back with. They say, well, GB3 works very well. This is this new model from OpenAI. It's transformed a very, very large, like 170, I think 5 billion parameter natural language model. And maybe a motivating example here, the main trained model of GPT-3 was tuned by an amateur on a small number of examples to summarize legal language. And so here it's taking in, upon liquidation of the company, et cetera, and summarizing it into plain English. And so this is the kind of thing that you would imagine that something that doesn't take into account the broader context couldn't do this kind of summarization or translation very well. But actually classical models, and there's many, many examples that are worth looking up, are doing a lot better than one might think. So the bar is pretty high classically. Oh, just lost lights. There we go. And so what's happening here? So you have these kind of seek-to-seek as a classical model. There's an encoder and a decoder. You start with some language on one side, you encode it, you pass some context through, and then you decode it. And it's not that there isn't some way of having context classically. So they break down this encoding stage to have different stages of recurrent neural networks, each of which that pass state through. So what you get is you're not doing some kind of word-to-word translation, you're taking into account the context of the previous words and then using that to generate some more. And concepts like attention that get learned allow you to figure out how to map from larger contexts of words into something that takes into account that context of meaning. And so the most modern, there's not time to go into all the details of this, but the most modern forms are really sophisticated examples of this. And so in my head, I think about it as in DisCoCat, we've got from some pre-group grammar or some grammatical structure, a rewrite that we put on top of sentences. But in a modern transformer model or a BERT model, that is all learned. So it's not that it isn't there, but it's all learned. And so now the question sort of comes that if classical methods do actually take into account context and do it in a somewhat more flexible way than a normal DisCoCat model, how can we still find advantage? One way is to just accelerate classical transformers. how to do this practically is an open research question. There's a lot of tools, things that have provable speedups that you could throw at this. Grover's is k-means algorithms, principal component analysis. Just the talk before this was on quantum topological data analysis. Maybe that hops in somewhere. That's exciting because it looks to be an exponential speedup. And then you have questions of, well, how are you going to load the data for this problem, and how do you load a corpus in? And if you're going to need to load data onto a quantum computer, then you're going to need a efficient quantumly loadable representation anyway. And so this sort of leads at least me to think that it's unlikely that the approach where you accelerate the classical machine learning method is going to be the most effective path for finding quantum advantage. You're probably better off looking for a model that is to some extent quantum-ish, because you're going to need to load that data in anyway. So DisCoCat is sort of the canonical example that folks have talked about a lot. And I think the challenge is to show that DisCoCat is better, that these compositional models are better empirically. And so one thing you can do is you can run it classically and see if it does better, but you're sort of caught in a bit of a bind. If you can run it classically, then that might be great from an NLP perspective. But then you maybe don't need the quantum bit. So you need to be in some place where you can run enough of the model empirically to motivate that it might be better, but you probably don't have access to a good enough quantum computer to run the empirics to show that it's definitely going to be better. And this is why there's a need for, I think, quite a bit of theory in trying to figure out what's going to be better before we have access to the hardware. And so there's been focus on special tasks where it might be better, some of which I actually learned more about today. So things like negation, ambiguity, and this recent, I'll highlight one that Martha mentioned that I think Martha Lewis mentioned in her talk earlier. There's a master's thesis by Francois Meyer, and then there's going to be an archive paper coming out where they do compare against BERT models and compare against classical state of the art. And in doing this, you want to extend DisCoCat to mitigate some of the disadvantages. So adding things like density matrices and stuff like that. And maybe one example I'll throw in is that a criticism of DisCoCat that I've heard is that it requires you to have this exactly specified rewrite for the grammatical structure of a sentence, but you could fuzz this out. So currently DisCoCat needs an exact parsing of the grammar. So something like, visiting relatives can be boring has, you can type it in a couple different ways. So, visiting could be either a noun, if it is the activity of visiting the relatives that's boring, or an adjective, which is that relatives who are visiting you can themselves be boring. And so in sort of the same way that we add switch to density matrices for meanings of words to allow some probabilistic mixture over the words, you could have a probabilistic mixture over the grammatical rewrites as well. And so this gives you a distribution over the categorical diagrams in the same way a distribution over circuits. And so these become mixed states. And so you should probably be able to mix in some version of this to do maybe like a mixed state, sort of a fuzzy grammar rewrite version of DisCoCat. Would this be better? I'm not sure. Maybe someone's already working on this, and I haven't thought about it that much. If so, I'd love to hear from you. So let's assume that we've shown that DisCoCat is good for some NLP tasks. If that's the case, how can we show that using quantum computers for it is better than any kind of classical model? And here, running on very, very small quantum hardware is not likely to be sufficient. You're not likely to have enough qubits available or enough gate depth to really run a sophisticated NLP task in a way that you can benchmark against something like classical state of the art, like GPT-3. So and another hypothesis that I suggest here is that DisCoCat circuits probably need to be highly entangled if they're going to be something that's not efficiently simulable by some classical method. And so examples here are these sort of different like matrix product state simulation methods or other tensor network methods that even if you're in a very large tensor product space, can allow you to approximately efficiently simulate how these circuits will compute. And in particular, if you are just looking at the sentence level, I'd worry that you might not have, they might not be sort of long enough to generate entanglement, but the larger conceptual hunks of words and like documents or paragraphs or sentences might be. And so one thing that I think would be useful to look into, or I would suggest looking into, is, can we show that if you look at DisCoCat models over a space of, if you take like lots of documents and you build circuits that correspond to those, correspond to that text, then how does entanglement spread throughout those circuits? Is there a lot of entanglement? Is there a little bit of entanglement? And my conjecture would be that there probably would be enough that it wouldn't be classically easily simulable as you make the model larger and larger. So another thing to do or to mention is that there's the trick that's happening in DisCoCat is not necessarily one that is just confined to natural language processing. So if you zoom out broadly, DisCoCat is an example of applying algebraic structure onto tensor product spaces. So we make this trade-off where we move from just having vectors to having tensors so that we can do contractions that allow us to have algebra on top. And the question there might be, are there other examples besides natural language processing where adding structure to your vectors is actually a useful thing? So is there like similar things to grammar that pop up in images or audio, or in particular things where you're in a very formal domain already where you want to do algebraic things? And there's been some work, this was from a couple of weeks ago, on using GPT-like models for automated theorem proving. And so here, there might also be some, a reason to bring back in the algebraic structure in a very formal way that can't just easily be learned. So to summarize, just some quick open questions from this talk. Is there a subroutine in classical state of the art, which for this I'll call Burton transformer models, that admits a provable quantum speedup? Can we show evidence that there are special NLP tasks where DisCoCat or some other quantum-ish model will beat classical state of the art? Does extending to fuzzy DisCoCat make things better? Can we show that entanglement does not spread fast enough to avoid DisCoCat models being classically simulable? Or on the other side, does it spread fast enough that there's quantum advantage to be found there? And I'd conjecture that that's probably going to happen. So to summarize, and without further ado, there's really I see two paths and frameworks. Can we accelerate classical methods without a large QRAM and without relying on empirics that are inaccessible to today's hardware? Or on the other hand, introduce new and better quantum methods that do the same things. And I really enjoyed all of the talks that I've been able to see today and see all the progress in this space. And if you've got ideas here and that hit these areas, I'm looking forward to seeing you at Bob's Pub in a couple minutes. Thanks.
Thank you, Will. I'm gonna give 1 minute for questions to appear in the Slack. Meanwhile, I think I should ask one. You're getting a lot of claps. Clapping online is a bit awkward, but thank you again for the talk. So let me ask a question about not being able to classically simulate the entanglement structures that are generated by these networks that are created by large texts that you're imagining.
Yeah.
So one obvious question is, how do we do it as humans? I mean, I don't expect the brain to be a quantum computer.
Yeah, I don't either.
But yeah. I am able to read a book, right? I mean, you could say, yes, we do it, but still it's kind of hard. I mean, we didn't evolve to be able to read. It's just something that was a tool that we made up. So maybe using a quantum computer, we can process text even faster. Then a classical computer can do it fast as well, faster than a human. So it's not about humans anymore. It's about just classical versus quantum computers competing, right? So how does this question of how do we do it fit into this, or it doesn't at all?
Yeah, it's a good question. I think it depends on what you're trying to do. I mean, are you trying to build a computer that mimics what humans do, or are you trying to build a computer that does a particular task really well, which actually might be something that humans can't do. So maybe,
Can you think of a task like this, an NLP task that humans cannot do?
It's a good question. I don't know. I know in other areas of machine learning, there are benchmarks where computers achieve superhuman performance. So if they ask people to identify in image recognition, this stuff comes up quite a bit.
Yeah, I mean, I get it if it's cancer, patterns in X-rays and stuff, but if it's NLP, it gets a bit trickier and philosophical, right?
Yeah, it definitely does. But I don't think we should be too anthropocentric maybe about what language meaning is.
Sure, yeah. I mean,
maybe language has meaning, even though we've mostly been the ones wielding it and creating it. Maybe there's meaning that we miss.
Oh, okay. So some stuff appeared on Slack. Thanks for answering my question. So Ross says, I agree with everything that you said in this talk. So great. Stefano asks, what kind of benchmarking techniques do you have in mind, if any, to estimate the amount of entanglement generated by a sentence?
Yeah, so the major comparison that I have in mind is that so it's sort of similar to what people look at with these random quantum circuits to show that they generate and spread entanglement. So you could take, if you have a bunch of quantum circuits, you could try and build a matrix product state model of those. So in the matrix product state models, you basically do SVD at every single time you apply a 2-qubit gate so that it cuts the space of the simulation to drop the singular values that are small. And then you can ask, what is the error between so these matrix product state simulations are entanglement limited. Like you only allow that's one way to think about it. You only allow entanglement to spread a certain amount. And so you say, well, if I run quantum circuits using entanglement limited simulations and I compare them to entanglement unlimited simulations, how big is the error? And I think, and I'm being a little bit vague about the error in what. I don't know if you would say an end-to-end natural language task, maybe. Maybe you could make it more modular and say, what's the error in the final state? Just the state fidelity. That would be maybe the place to start. So like what do circuits that have, the caps and cups that come from DisCoCat end up having long range entanglement or not?
Yeah, indeed, the measure that you use, it really affects the conclusions that you will draw. For example, Ross indicates something which is a bit counterintuitive, but it's true. Being highly entangled does not imply hard to simulate. Like, for example, free fermion states can be maximally entangled if you want. They can reach the page entropy of a given Hilbert space dimension, but they're, or stabilizer circuits. So yeah, maybe you can look at other stuff beyond entropy, like, entanglement level statistics and stuff from quantum chaos. What else?
Yeah, I think it's just I'd say it's more, Ross's point is totally a good one. And there could be definitely other, the broadest question is, how quantum are DisCoCat models? Like if we really look at the sentences that exist in the real world, how much either contextuality or entanglement or some kind of benchmark, how do you measure that?
Exactly, it's a good question. So Gianluca Anselmetti, they ask, where do you see the possible main value created in finance by quantum computing, besides just monetizing a small advantage over competitors in, for example, high-frequency trading or portfolio optimization?
Yeah, so we actually not looking so much at high-frequency trading type stuff, but a lot of things are in risk models and risk calculations. So right now we're looking at Monte Carlo simulations sort of broadly, which comes up all over the place. But if you have some model for what some financial contract is going to be worth, depending on econometric assumptions about how the economy behaves, then that allows you to price that contract. And that's based on how much you want to understand through, at a really high level, you're using computers to tell you how risky is some contract. And if you get that wrong, that can have consequences for all sorts of people. it can affect how much money you make, but also it can affect how stable some economic system is. And so better simulations so in particular in derivatives pricing is where we're focusing right now. Portfolio optimization is similar, but there are also risk calculation on top of portfolio optimization as well.
And I guess classically they are hard too, right? Like doing inference in general is hard.
Yeah, so it's an interesting example where classically a lot of this stuff it becomes hard immediately, but there are decades of ways of simplifying the problem to make it easy. And so then you have to ask the question of, how much better do you get from going from the simplified problem to the perfect problem? And is that improvement good enough to justify whatever the 10 or 20 years it's going to take to build a quantum computer good enough? Hopefully less, but it's justifying that gap that I think we kind of all need to do in looking for quantum advantage.
Cool. Jean Longtan asks, are you guys doing any stuff on quantum Monte Carlo at Goldman? It's quite a general question.
Yep, lots. There will be papers when we finish them up.
And Adriana asks, and well, she doesn't ask. She says, an NLP task that computers might do better than humans is author identification. Just throwing it out.
That's a good suggestion. Yeah. Or maybe style transfer, right?
Yeah, like they do for paintings, right? But this is more hardcore, I guess.
Yeah, right. Like anyway.
And I see Stefano is typing something. I'm waiting for him to type. By the way, feel free to join the Slack later and just answer more questions or just participate in.
I'm actually on the Slack now, I think. So shall we head to the pub then?
I think it's time. Yes, I think it's time. You seem thirsty. Okay, let's thank again the speaker and let's answer the rest of the questions on Slack. Thank you again for your talk.